When there's a thunderstorm going on, how come you can see the lightning instantly, but the thunder has a delay? Sound waves are mechanical waves, so that means they need particles to move. They need a medium to travel through. That's why you can't hear in space, because there's no air to travel through, there's no water to travel through. It's also not a transverse wave, it's a longitudinal wave. A transverse wave looks like this, and as this wave pattern travels through the medium, like air, the air particles oscillate perpendicular to the direction the wave is traveling in. Longitudinal waves, like sound, the molecules vibrate in the direction that the wave is moving. And when graphed, they don't look like this. They look more like plotting points of density and rarefaction. So areas with higher compression have higher pressure, and areas with rarefaction have lower pressure. It travels as a pressure pattern through a medium. And your ears collect these air pressure changes, and your brain decodes them and translates them into what you call sound. When sound is traveling through air at 0 degrees Celsius, the velocity it travels at is 331 meters per second, approximately. But as the temperature increases, so does the speed. Why? Because warm air has faster molecules, and faster molecules means faster chain of collisions. More collisions per second means faster wave transfer. So this is the speed of sound moving through air at 0 degrees. How about 20 degrees? There's actually a formula, which is 331 plus 0.60 multiplied by T, with T being the temperature in Celsius. So at 20 degrees, it would be 331 plus 0.60 times 20, which is 333 meters per second. Compared to at 0 degrees, 331. When it travels through different mediums, it will also have a different speed. For example, air, it's approximately 333 meters per second, or 343, sorry. When it's traveling through water, that's my water droplet drawing, roughly 1500 meters per second. When it's traveling through steel, it's roughly 5000 meters per second. You might think this looks backwards. Water is more dense. Why does sound go faster through it? This is because there's a formula for the speed of sound based on the medium. You don't need to know this, but it's V equals the root of this B over density. This represents stiffness. So what that means for us is that when stiffness is higher, speed is higher. When density is higher, speed is lower. Steel is more stiff than air, so sound is faster traveling through steel. That formula is also on the cheat sheet. Let's go through an example. Let's say you see lightning strike on a building, and then 5 seconds later, you hear the sound with your ears. That's you with your ears. We know the speed of sound is roughly 333 meters per second. And distance is found by multiplying speed and the amount of time it's traveling, which is 343 times 5, which means that this lightning was roughly 1.7 kilometers away. So by looking at the lightning and then counting how long it takes to reach you, you can find how far away it was. Here's a tip, a general rule of thumb, which can be fun in real life. Every 3 seconds is roughly 1 kilometer. What's the difference between pitch and loudness? Pitch, as a wave property, is frequency. And frequency is measured in hertz, which is cycles per second. So it's not how long something takes to vibrate, it's how often it vibrates. If the pitch is high, for example, someone whistling, then that means fast vibrations. If it's low pitch, like a bass drum, slow vibrations. That's pitch and frequency. How about loudness? What's loudness represented by when it comes to waves? It's represented by intensity. I did make a video previously on intensity, but I'll cover it here briefly. Intensity is how much energy is transferred every second per unit area, and it's related to amplitude, which amplitude is the peak height of a wave. It's related to amplitude, but the perceived volume is very complex. There's factors like your ear biology and sensitivity. The math behind it is logarithmic. But just know that loudness is related to intensity, just like how pitch is related to frequency. Humans have a range of frequency, which is 20 hertz to 20,000 hertz. So anything below or under this range, anything outside, we can't hear it. Below 20 hertz, what's some stuff that happens below 20 hertz? It's called infrasound or infrasonic sounds. For example, earthquakes or machines that vibrate. giving off waves. This gives trouble to workers operating near these kind of machines because even though you can't hear it, it can still cause damage to you. If something's above the frequency of 20,000 hertz, we call it ultrasound or ultrasonic. These are BATs and medical imaging. Like, when you're pregnant and you want to see your baby, you get an ultrasound. This makes studying 10 times easier. Go download the free cheat sheet in the description and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.